Hello. Yes. Hello. Can you hear me? Hello. Yes. Good. Oh, hey man.
Good to see you.
Good to see you as well. So many familiar faces here.
Yeah, I know. Have you given a talk in this building before?
No.
It's very
Very
nice.
fancy here.
You haven't been to this building? You must have been to this building.
Oh, this room. I've been to this building. There's a new CS building, or this is the new?
New is like in 2029. They're trying to build ones, but they're failing.
Cornell is midway.
Yeah, lots of, yeah, I'll tell you.
Yeah, sure.
One is one program is Bosch. Today we have the pleasure of welcoming Eshan from Cornell University. Probably interested in DCS. Today we'll be talking about his work on.
Thanks so much for the introduction and inviting me to the Princeton theory seminar. And I'm pretty impressed. All of you start on time at Cornell. Usually it's +5 despite our best efforts. So today I'll be talking about a series of papers where we are trying to understand these things called adversarial sources. And this is joint work with Jesse Goodman, who just graduated. He was a PhD student with me. Most of the cool ideas behind the series of work is actually by Jesse. And he'll probably be on the job market next year. So if you're looking for a good theorist, please look at his application. The other people are Vipul, Shin, and David, who generously contributed to this project. Okay, so let's start off with randomness, which turns out is really useful in computer science. It's useful in a bunch of areas. So it depends, if you're a cryptographer, you use randomness. If you don't care about cryptography but do game theory, you use randomness there as well. So it's a really, really powerful resource in computation. And a nice example that I like to give is random sampling, where you have many people who are voters in an election, and you quickly want to get a sense of how this election is going. Then you'd probably sample maybe 400 people, and then randomly sample 400 people, and then just Chernoff bound gives you that with pretty high certainty you have the output results with some amount of accuracy. Also, another example of randomness is in randomized algorithms, which all of us have seen. In particular, this is a really interesting and important problem in computational complexity theory, which is called as polynomial identity testing. Many natural problems can be reduced to this, and the problem is as follows. So you're given two polynomials, P and Q, multivariate polynomials, and you just want to check if, as formal polynomials, they're same or not, right? So, so it really depends on the representation of the polynomial. So if I give you the polynomials, the input as just a list of coefficients, then this is easy. But if there is some, if they are presented as arithmetic circuits or formulas, then it becomes much trickier. The naive algorithm of just expanding everything out becomes exponential. And, or equivalently, you could ask, given a polynomial, if it's the identically zero polynomial. There's a simple randomized algorithm for this, which is, just evaluate this polynomial over a random point in a large finite field, and use the fact that low degree polynomials have few roots to get that your randomized algorithm succeeds with high probability. Okay, and it's a major open question if there's a deterministic algorithm for this question, and it's perhaps one of the central problems in algebraic complexity theory. Okay, so more generally, one could ask, in the use of randomness in algorithms, is there an efficient, deterministic algorithm given any efficient randomized algorithm? Or do we need randomness in computation, in efficient computation? This is posed as the famous BPP equals to P question. And in particular, do you even need to buy or read this book called Randomized Algorithms? And similarly, you could ask this question in the space-bounded setting of whether BPL is equal to L. Is randomness useful in saving space or not really? And there are famous examples of algorithms, both in the time-bounded setting and the space-bounded setting, where a randomized algorithm was found, and then some very smart people came up with ways of de-randomizing it or showing, algorithms which are deterministic and do the same task. So this gives some evidence towards the answers probably being equal to. And then Nissan and Avi gave us really compelling evidence that under plausible circuit lower bounds, probably BPP is equal to P, and you do not have to read this book. But no, that's just a joke. This is a beautiful book. But in cryptography, so the point was there, randomness may or may not be useful in computation, but we are really good at coming up with randomized algorithms. In cryptography, you really need randomness in protocols, in zero-knowledge proofs, and so on. And here, one can cruelly show that you really need randomness. And the question is, how do you generate random bits? And it turns out, there are various sources in the nature where you collect random bits. But what has been observed is that you do not get independent IID perfectly random bits, and they're a stream of correlated bits. And unfortunately, applications do need purely random bits. Basic protocols like commitment schemes and other things fail, assuming, even if you have access to a stream of bits where each bit brings in fresh entropy, but is not completely random. And most randomized algorithms you analyze are actually with respect to purely random bits. And here's some, don't ask me much about this, but apparently Bitcoins lost a bunch of money because of using faulty randomness. So all of this is to convince you that we really need to care about randomness extractors, which are efficient algorithms that translate entropy sources, so defective randomness, into purely random bits. And it turns out that the use of extractors as defined is for, taking defective sources of randomness and spitting out purely random bits. But the definition has gone way beyond its initial use, and it has found all sorts of interesting applications, like the best known circuit lower bounds are against these things called affine extractors. Two-source extractors give you Ramsey graphs, which are central in combinatorics. It's useful in sampling. It has non-trivial connections to coding theory. It's useful in crypto. It's useful actually in removing randomness, which is kind of counterintuitive. So these are cool objects, and it has lots of nice connections to different areas in mathematics and theoretical computer science. Okay. With that, let's actually start trying to model what a defective source is and what should we construct randomness for. So the first first attempt would be of using Shannon entropy, which is the most well-known way of measuring randomness of a random variable. But it turns out for the setting that we are thinking about, that we just get one sample from some distribution and we want to spit out uniform bits. Shannon entropy is too weak a notion, and just having a guarantee that a distribution has Shannon entropy is not enough. And the example that's given is a distribution that's with 0.01 chance it's uniform on n bits, and with very high probability, with 0.99 probability, it's just a fixed string, all zeros. Okay. So your extractor is, it cannot use any randomness of its own. It's a deterministic function, right? It's a mapping, say, from n bits to maybe just you're trying to output 0, 1. So whenever it sees the all zero string, it either outputs 0 or 1. So it's going to output whatever the output on 0, 0, n is with chance 0.99, and you cannot output, a fair bit, right? So the typical way of, okay, and observe that, this has really high Shannon entropy, but you cannot output even one really random bit. And the stronger notion of mid entropy is actually more useful here, which is the way of thinking about it is a distribution has mid entropy k if on any point on its support, it assumes that with probability at most 2 power minus k, right? So no point is too likely in its support. So it's not hard to see that, we'll talk about distributions on n bits. It's not very hard to see that the min entropy is going to be between 0 and n, 0 being when it's a point distribution and when it's completely uniform on n bits. And we'll talk about n comma k sources, which are distributions on n bits, and they have min entropy k. By the way, please feel free to stop me for any questions. Okay, and so for most arguments, whenever we talk about n comma k sources, we'll actually think of the distribution as a flat distribution. So it looks like this. It's uniform on some subset, unknown subset of size 2 power k. Okay. So it turns out that a general n comma k source is a convex combination of these things. It's not a very hard thing to show. Okay. Informally, an extractor outputs uniform bits from a weak source. And this is the picture that we have. So the key point is you cannot design an extractor that depends on the source X. Rather, you're given a family of distributions, and you need one extractor that works for all of them. Okay. All right. So, and so it turns out it's too much to expect that the distribution is completely uniform. We'll be okay with approximately uniform, where approximately is the statistical distance, which is half of the L1 distance of the two distributions. Okay. Unfortunately, it turns out that there's some bad news, which is you cannot even extract assuming min entropy guarantees. So you cannot even output one bit from the class of all sources which have n-1 min entropy, right? So you cannot have one extractor that works for all sources with min entropy at least n-1, which is pretty bad news because min entropy is between 0 and n, and you're saying even almost full doesn't work. And I'll show you the proof because it's really simple. You assume an extractor that works. So the extractor is a deterministic function, right? It takes n bits, it outputs either 0 or 1. And so it has to assume one of the preimages. So the preimage of 0 or 1 has to be at least of size 2 power n-1. And you adversarially choose your your distribution to be the one which is more popular. So it looks like this. Say, this is all the points on which the extractor outputs 0. So, the size of this set is more than 2 power n-1. So the distribution which is uniform on this has min entropy more than n-1. But by our choice, the extractor on this distribution is always 0, right? So the main point that this works is that your extractor cannot depend on the source. Rather, it should work for all the sources. So you adversarially choose a source that it doesn't work for. Does this make sense? Yeah. Okay. So this is bad news, but what it turns out that for the last several decades, people have said that, well, okay, this is not possible, but maybe assume min entropy and a little bit more structure, and then a lot of cool things are possible. So the most simple set of sources probably is bit fixing sources, where it's a distribution on n bits, where some unknown set of bits are independent and uniform, and the remaining bits, say, are constant. Right? These are called as bit fixing sources, and it's not hard to see that if you just take, say, parity of all the bits, then the output is uniform. But you probably may want to output more bits, and then it turns out you can do interesting math. You can use expanded graphs and so on to extract. A really popular model is independent sources, where you think of your X as actually comprised of many independent sources, X1 through Xn, X capital N, where each Xi is a min entropy K source. And it's realistic in the sense you could think of various different unrelated sources giving you randomness, and then you're trying to extract a few bits. It turns out algebraic sources, affine sources, are interesting because probably not realistic, but they give rise to nice circuit lower bounds. It actually also generalizes bit fixing sources. Or more complexity theoretically, you could say that, well, maybe nature is a low complexity algorithm, and it has access to purely random bits, and by a low complexity algorithm, it's outputting a weak distribution. Okay. It's the number of classes of sources that have been studied is beyond the scope of this talk. So today we'll kind of focus on mostly on generalizing this model, and it has nice applications to this as well. Okay, so the independent source setting is the following, that you have capital N sources. So typically in extractor talks, capital N stands for 2 power n. That's not the case here. Capital N and small n are unrelated things. In fact, think of capital N as pretty small. So the extractor gets samples from x1, x2, till xn. All of them are independent, and we know that all of them have min entropy k. And you're trying to output, purely random bits or statistically close to purely random bits. So this setting has been studied a lot. And what's known here? What's known is, if by a long line of work, that you can actually extract from 3 independent sources with pretty much really great parameters. So min entropy, polylog n, error, that is closeness to the uniform distribution, being exponentially small in the min entropy. So these are, so you can show that you cannot go below min entropy log n. So this is really good parameters. Okay, the capital N. Yeah. Yeah, that's just 3 here. Yeah. Yeah. Right. And so there cannot be any one source extractor that we saw the proof, but it turns out you can have 2 source extractors, just probabilistic method works. Here, for low error, so this paper by Shore and Goldreich kind of started this work on independent source extractors. So for 2 source extractors, if you insist on the error being low, then unfortunately this is not, not great. You ideally want this to be much smaller, existentially like log of n over epsilon. So, and for crypto applications, what you need is epsilon being negligible. So something that's, decays faster than a polynomial. But in the high error regime, some work by me and David and a series of works recently got this down to polylog n with polynomially small error, or actually just constant times log n with constant error, and this is a really nice work of Shinli, recent work of Shinli. This is pretty close to the existential bounds, which is probably like log n plus O of 1. And the significance here is these translate into Ramsey graphs. So this implies a polylog n Ramsey graph, which will probably feature later in the talk. Yeah.
The first result, is that a lower bound?
Uh,
When you say, or like it's a construction which use at least 0.44 n entropy source.
right. The construction uses at least. Yeah.
And there the Fabian significance still shows that polylog n is possible.
So the way I wrote here, so the dependence of k is like log n over epsilon. So you'd probably, for this, you'd need like, omega n min entropy. But for applications, maybe you need like 1 over n power log n or something, and then you can do much better, like polylog n. Yeah, good question. Yeah, okay. All right, so the finally, yes. Right, really, that's a really good question. And sorry, I did not mention it here. You can get all of the like omega k bits out. Yeah. Okay. Okay. So finally, coming to the adversarial source setting, which is the topic of today's talk. So this generalizes independent sources in the following way: that we have capital N sources here, and some unknown of them are faulty. In the sense that let's assume all sources are still independent, but some sources contain entropy. Okay? So in the independent source setting, we assume all sources are independent and all of them are n comma k sources. But now we are going to this weaker model where only some of them contain entropy. And constructing extractors will be the focus for this setting, will be the focus of our talk. More generally, in our papers, we study where the faulty sources can actually have bad correlations with the good sources. But it turns out even just studying the situation where they're independent has all the construction ideas to lift to this more messier setting. So I'll just focus on the more cleaner setting here. And the reason for this, why study these sources? One is it's a realistic setting where many true random number generators or physical devices sometimes are faulty and give you samples that do not contain entropy. There are various scenarios in cryptography, like collective coin flipping and other things, where there are some adversaries, and this is what this setting reduces to. And in general, going beyond independence is something that has been recently studied by other people as well. So it's so there are other models like something called Shelah sources or somewhat dependent sources, which capture correlations between various sources in different ways. Okay.
When you say that only some sources contain entropy, do you mean that some sources may be very simple, or do you mean that some sources may be complex, but we'd like to know the randomness conditioned on the outcome of those sources? Right.
So we're actually saying something very simple, that these green sources that you see, these are n comma k sources. So they have min entropy at least k. But these may be, either maybe it's a fixed distribution or has min entropy k over 2 or other things. But we just do not know. So the extractor doesn't know which sources are good and which are bad. Good question. Okay, so it turns out that these adversarial sources come up in a natural way in a complexity theoretic setting for extractors, which is small space sources. So these sources are on n bits, and the assumption is that it's sampled by a low complexity algorithm, but the low complexity is the algorithm is memory bounded. Okay, so how do we capture this? Usually memory bounded stuff is captured by branching programs. So the width of the branching program, 2-power width, represents how much memory it has. Each each layer represents the state of the memory. And the source is generated in this way that there's an underlying graph with labels, either zeros or ones, and some probabilities of you doing a random. If you're here, you choose this edge with probability 0.1, you choose this edge with probability 0.4, and maybe this edge with probability 0.5. And if you choose this edge, you're kind of outputting this label. Okay. So the way you generate this source is you just start here and do a random walk and just output the labels that show up. Okay. So these are called as small space sources, which were introduced by Koenig and Maurer, and more formally by Camp, Rao, Vadan, and Zuckerman. So the source looks something like this, and it generalizes a bunch of things that have been studied before. And here is a very simple observation, which is, if I give you a source like this, and you just kind of partition the source into, say, L chunks, and let Wi be the state that you have reached after reading the ith chunk. So maybe W1 is maybe this state, W2 is this state, and so on. If you do a random walk, you just keep track of at the boundaries which state you're at. If you actually condition on which states you reach, then these different sources, the chunks, become independent, right? So suppose you do this random walk, and I tell you that condition on this thing, then it doesn't really matter how you got here for this source x2, right? Condition on this is independent, right? Yeah. Okay. So suppose you divide it into L chunks and you condition on all the boundary states. So each state, recall there are 2 power S states. So if you say condition on reaching here, you're kind of leaking S bits of information, right? There are 2 power S states. So you're kind of leaking what's the memory configuration here. So if you condition on L of them, you lose L times S bits of min entropy. If there was a nice chain rule for min entropy, which there is not, so there's some things under the hood, but this is what happens. So what happens is, conditioned on these boundary states, what you have ended up with is you started with a small space source. Now you have ended up with L sources, and you know that the sum of the entropies of these sources is K minus LS, right? Now you could just do some Markov or something and say that many of the sources have a nice amount of min entropy, right? So this is exactly adversarial source, as I showed you, right? There's a bunch of sources, and some of them have enough min entropy. Yeah. So if you can construct good adversarial source extractors, you get good small space extractors.
So just to get it right, Eshan.
Yeah.
Very small number of sources are in simple good. Most of them are faulty in your set.
Right. Yeah. Yeah. We'll get to yeah. Good question. Yeah. So what's known for small space sources? Well, existentially, great extractors exist is usually the story here. So think of S as maybe like polylog n, if it makes sense. So this term dominates. With a space n source, you can sample any distribution. So small space makes sense here. So maybe S being polylog n, then that's the term. So way off from the existential thing. Existential is maybe like O of log n. And the line of work on these adversarial sources setting kind of gets this improvement from 0.99 to square root n and negligible error. If you don't care about negligible error, but larger error, then some work by me and my student Junjay actually gets it pretty close to the existential bound of 2s plus log n times log n or something. And recently this log squares also. So in the high error setting, this question is kind of solved, but in the low error setting, there's still a huge gap. Okay. With this, finally, let's start talking about extractors for adversarial sources and what parameters we are interested in. So just to recall, if all of that was a blur, let's recap what's going on here. There are capital N sources. The green sources represent that they have some min entropy. Okay, they have min entropy K. The red sources are adversarial, meaning they're faulty. They may or may not contain any min entropy. We just do not know the locations. So there are 4 parameters here. Capital N is the number of sources. Capital K is the number of good sources. And N and K are just, for a good source, well, it's every source is on N bits, and the good sources have min entropy at least K. Okay. It's a lot of parameters, but is this kind of clear? What's going on?
So Eshan,
Yeah.
feel free to table this question.
Yeah.
Are results at least possible if you don't assume independence between the faulty sources and the good ones? Like if the faulty sources are just completely arbitrary, nothing to control.
Right. That's a really good question. So what if the faulty sources are allowed? Say there's just maybe one faulty source which is allowed to depend on all the things. So the answer is so that kind of goes to the setting of influences in analysis of Boolean functions. So these are more generally called as symbol fixing sources. It's in a different setting. So there, how much influence can one maybe block have on the outcome of a Boolean function? And the answer is that you cannot expect negligible error. You can do something, but you cannot expect negligible error. Yes. Yeah. So, right. So yeah. So in our paper, when we handle correlations, we allow that the bad sources can depend on only like a budgeted number of good sources, because otherwise you cannot do much. Yeah. Yeah. Okay. So with that, let's actually assume everything is independent. Some of them are good. The bad ones cannot depend. And say you just have 2 out of capital N, right? So you just have 2 sources. You do not know which ones. Can you design an extractor for this, right? Any ideas? So I think the most naive idea is, why not apply a 2-source extractor on all pairs, right? So suppose you apply a 2-source extractor on all pairs, and then maybe take, a bitwise XOR of the outputs. This actually works, it turns out, right? So that's amazing. And the proof is also really simple. So why does this work? So the extractor I'm kind of saying is this, right? So apply on all xij and just output the bitwise XOR. And the proof is, what do? So in the analysis, you kind of fix all the bad sources, right? So you want to show that for any fixing of the bad sources, the output of the extractor is still close to uniform, and then just convex combinations of uniform. So, okay. So you have fixed this, and then, so there is some extractor call, which probably is not, there is a picture. So this extractor actually hits the 2 good sources, right? So this outputs uniform bits to the XOR. So mathematically, like this looks like the good extractor call plus a bunch of calls which misses the good sources, right? Which are fine. You can, it's a fixed thing. Like, it's either, say we think of the extractor outputting as 0 or 1, and that's like just, XORing with a fixed bit or a fixed string. But then there are some, these kind of annoying things which can potentially spoil that, right? But it turns out, if you just say, look at this random variable, which is the XOR of the two extractor call on X1 and all other sources not being the good source XR. That's a random variable of length M, right? Output of the extractor being, of length M. And it's just a random variable that depends on X1, right? So this leaks M bits of information about X1, and you can just, fix it, and X1 loses M bits of min entropy. If there was a chain rule, but with like plus logs, there is something you can do for min entropy. And if you assume that, your output M is like, say, K over 2 or something, then, X1 still has min entropy, right? So similarly, you fix this as well. And so you have leaked some information about X1. Oh, this should have been XR, the first one. Sorry for the typo. So you have fixed some, min entropy about X1 and something about XR. Everything else is fixed now. And now we know that, the two-source extractor still works, right? You just have to choose a two-source extractor that works for min entropy K over 2 for whatever K you choose. So how does this work? You say, assume, so we are trying to extract from n comma k sources, choose a, two-source extractor that works for min entropy K over 2, and choose M to be like 0.1 K or something, right? Does this make sense? Sorry? Right, sorry. So I should have mentioned this. So M, I'm assuming, is the output length of the two-source extractor. So the key thing that's going on here is that we are not fixing individual, 2xt of x1 with x3, 2xt of x1 with x4, and so on. Then that would lead to, a dependence on capital N. Instead, we are saying, well, we could just fix the parity. And, that's how we save, right? Okay. Yeah.
Nothing is logged if I just assume that your extractor output 1.
Sure, yeah.
And then it's just like
Yeah, even with 1 and M is not really different. So yeah, right. Yeah, nothing changes with just, so you could as well think instead of M, just 1 bit. Yeah, right. Okay, so what we have proven is that, if you give me a two-source extractor that works for min entropy K, then you can handle N comma just 2 good sources with N and O of K min entropy for adversarial sources, right? Maybe like 5K, or maybe K plus 10 if you just assume 1.
Sorry, could you explain how you save when you lose some information, how do you save it?
Right. So as Pravesh said, let's assume that two-source extractor just outputs 1 bit, right? So this is just 1 bit of information about X1, right? So let's say you fix that random variable. So that random variable says a 0 or 1, right? So conditioned on this random variable, X1 still has min entropy K minus 1, right? By chain rule or whatever. So you just have to take a two-source extractor that works for min entropy K minus 1. Yeah. Okay. So this is really nice, but it turns out, unfortunately, we do not have good two-source extractors for negligible error. So a lot of adversarial source extractors, the motivation comes from crypto, and here we are constructing higher things. So unfortunately, this is a really nice construction. It works if it gives you low min entropy if you settle with high error, but if you want negligible error, we do not know how to construct good two-source extractors. Okay, so we have great 3-source extractors, right? So maybe assume, like, instead of 2 good sources, assume 3 good sources. Can we do it, right? Okay. So you have 3 out of n good sources. Any guesses for what, how can you extract from this? All triples, right? Perfect. Apply 3-source extractor on all triples, and then take the bitwise XOR. Unfortunately, this doesn't work. Okay, sorry, I asked, does this work? It doesn't work. And the reason is that let's try to do the analysis again, and you fix all the bad sources. And then, unfortunately, you have extractor calls that looks like the red one there, which hits 2 good sources and maybe 1 bad source, right? So if you try to, so what were we saying? We were saying there's a good extractor call, which hits all the 3 good sources, and will fix the parity of all the other extractor calls, right? But even if you just try to fix the single 3 extractor, which hits 2 of them and doesn't, hits 1 bad, that leaks joint information about R and N, XR and XN, right? So if you fix such an extractor call, then 1 R and N cease to be independent. So the good 3-source extractor will not work, right? So unfortunately, even though we have good 3-source extractors, at least this analysis doesn't work, and we do not know how to show that it works. Okay. So yeah, exactly. It's not clear on fixing this that the good extractor works. But it turns out this gives you enough leverage to actually come up with a framework where you can make this work. And the framework is kind of interesting. So let me show you the framework. So our goal is, extract with negligible error from n, k, little n, polylog n sources. So low min entropy. And we are trying to minimize the number of good sources, right? So the idea first is, lay out a hypergraph on all your sources, okay? So something like this, right? So earlier we were saying, choose the hypergraph which contains all 3, the 3 uniform hypergraph with all edges. And then we were applying like a 3-source extractor on the hyperedge, and then combining it with like a global function, which was the XOR of all things, right? So this is just, the earlier thing was just an instantiation of this framework. So it turns out by choosing the hypergraph carefully and the local extractor carefully, you can make this work. Okay, so the observation is the following. Let's suppose the independence number of your hypergraph which is represented by alpha of G, is less than the number of good sources. So the independence number is, the minimum number of, the maximum number of source nodes that you can have without covering a hyperedge, right? So suppose, the number of good sources is more than the independence number, then you know that at least one of the hyperedges has hit all the good sources, right? And then your local extractor works, right? So the idea is construct such hypergraphs with low independence number. And then the analysis would be just, fix all the bad sources. And good question, you're ahead of me, yes. Right, so yeah, one more slide, Avi, then I'll get to you. Right, so you need something like, as Avi pointed out. And what do? You kind of treat these calls, the other hyperedge calls, as leakages on these good sources, right? This is what was happening, but as the construction, we saw that one hyperedge contained 2 of them, and it leaked joint information about them, right? Okay, so what hypergraphs can we choose? It turns out designs is exactly what you want, as suggested by Avi. So what's a design? It has 3 parameters, N, R, and S. It's an R uniform hypergraph. And the pairwise intersection of these hyperedges is strictly less than S, okay? And explicit designs have been used in really influential papers on pseudorandom generators and extractors. So for us, we'll need designs with a slightly different property, that it also needs small independence number. we don't care so much about the number of hyperedges, which was what was required for PRGs. Yeah.
I don't think you can avoid having two good and one bad source triples. So is the idea that the design would minimize the number of the triples in some way and the analysis will go through? Is that what you're going to?
Great question. You'll see in a bit. Yeah. Okay. So, and the independence number is the largest thing. So here's an example of a N32 design. Okay. So it's on. So the hypergraph is on N nodes. It's 3 regular, and no 2 hyperedges have intersection more than 1, right? So, and it's a simple observation, and the observation is take all lines on the vector space F3L. Okay. So you know that any 2 lines cannot intersect on more than 1 point. And the independence number of this graph, luckily for us, have been studied by really cool combinatorics people, and it's exactly what's called as a cap set. So bounds on cap set tell us that the independence number is something like this, n power 0.923 or whatever. Existentially, there are better N32 designs, but we do not know how to construct them. And plugging this into our framework, we'll apply a 3-source extractor on lines, right? So the intersection is at most 1 now. So we are good that you're not doing joint leakages. And then just combine it with a regular XOR, right? So the analysis that we wanted to do on all pairs, instead we are saying just do it on lines, and then it works. But still, you need a lot of good sources, right? N power 0.923. Whereas existentially, we know just 2 good sources or 3 is possible. But is this kind of clear? Okay. It turns out we can do better. And this is the extractor. It turns out we can do better. So in fact, it was shown probabilistically that if you want general n(r)(r-1) designs, so these are designs. So these are hypergraphs which is slightly non-trivial, right? Like it's saying that the intersection of any 2 hyperedges is at most is strictly less than r-1, so it's at most r-2, right? It's the bare minimum to from triviality, which is just r-1. And there, so think of r as a constant, like a large constant. There should be no s here, but it's saying that you can get existentially there are good designs with independence number n/1/r. But this is existential, and using some connections to coding theory, we actually could construct such designs off by a 2, but it doesn't really matter because we'll choose r to be a large constant. So plugging this in, so what we do, we choose r large enough such that capital N power 2/r is smaller than k. But now we have joint leakages, right? Like there are some things which are, leaking information about r-2 of the sources, right? It turns out in a joint work with a bunch of people, we actually constructed such extractors which can handle such joint leakages on less than r, so r-2 sources. So for low min entropy, and this is actually based on multi-party communication lower bounds. So if you could allow joint leakages on r-1, that's kind of the number on forehead model. This is slightly weaker. You're saying r-2 parties can jointly leak. So there's a very simple and direct connection to communication complexity. So that's the extractors. That's the local extractors we'll use. We'll use leakage resilient extractors on the local hypergraphs, hyperedges, and then just combine using XOR, and the proof works, right?
So if you could handle leakage on r-1 sources, that's the basic construction, right?
Exactly. Yeah. Yeah. Okay. So plugging everything in, what we have is we can handle n power delta, n log n sources for any constant delta, because we can choose this, in the design parameter R, we can choose R to be as large a constant as we want. Okay. So in the last few minutes, I'll tell you about some recent work which is not yet published, which is in progress. But yeah, as you may recall, k equals to just 2 good sources still suffice. Oh, sorry, yeah. Right, so that's a really good question, and that has to do with like our leakage resilient extractor. It's based on, it's kind of a reduction from multi-party. Yeah, I think you can make it log n. Yeah. Okay, so it turns out we can do actually much better now. So this was n power delta, but we can actually get it to polylog n. So this is work in progress that's going on. And the way we do it is by using something called as two-source condensers. So a two-source condenser is weaker than a two-source extractor. And what it says is, if the function gets 2 independent sources, n comma k sources, instead of outputting fully uniform random bits, it outputs a super high, like very high min entropy source, right? And it's actually not like a high entropy source, but in reality, it's exponentially close to a high min entropy source, but let's, ignore that. But this has been constructed by really nice work by Benara, Cohen, Doron, and Tashma. And the key thing is the condenser has exponentially small error, which the two-source extractor doesn't. So the idea is the following, that we'll choose a suitable graph now, not a hypergraph, but a graph, and apply a two-source condenser on all the edges, and then combine it with a global extractor. So something like this, just lay out a graph, apply condensers on all the edges. And it turns out what we want to actually hit is a wedge, is a good wedge. So a wedge is something that it's like an incomplete triangle. So one of this thing is missing. And if we can assure that, no matter how the good sources are located, the graph, just the guarantee on the number of good sources, we hit like a wedge. And it turns out we are good because of the following, that we'll fix all the, sources outside the wedge without destroying, because everything is independent. And now, if we look at, our extractor, which is on all edges applying the two-source condenser, then the two-source condenser works on this and gives you really condensed sources. And then it has some edges which just, have x1, some edges with just x2, some edges with just x3, and then something which just misses all of 1, 2, 3, right? And now what we'll do is we'll fix these leakages. So as before, it's the parity of a bunch of things. We'll fix this, and x1 loses min entropy. We'll fix this, x3 loses min entropy. We'll fix this, x2 loses min entropy. But that's still fine. And now we'll use the fact that the two-source condenser is actually strong. Meaning even, it works even if you fix one of the sources. So with high probability over x2, the output of the condenser of x1, x2 is actually a high min entropy source. Okay. So all of this is fixed, and then you have on the top like the sum of 2 independent sources, both which are very high min entropy. So it's just like A plus B, where A and B are very high min entropy sources. It turns out these things are called sum-set sources, which have been studied, and just applying an off-the-shelf sum-set extractor. So in this high min entropy setting, it turns out you don't need like sophisticated sum-set extractors, just inner product works. You could just apply inner product on you. So the whole extractor will be inner product of sum of all condensers. works. So, and finally, I need to convince you that you do hit a good wedge. And let's call that wedge independence number. The claim is that the wedge independence number is bounded from above by the size by the independence number and the clique number. I'm not going to prove this. I'll leave this as exercise because, okay, so maybe the hint is a wedge independence. If you're trying to come up with, a graph with large wedge independence number, it looks like a collection of disjoint cliques. And you cannot have too many disjoint cliques if your independence number is not too big. And it turns out, what's a graph with no large independent set or clique? It's a Ramsey graph. Luckily for us, Shinli constructed really good Ramsey graphs last year. So just plugging that in, we can just take this capital K to be polylog n. So plugging everything in, we get a two-source adversarial source extractor for n polylog n sources with n log n. Still, this is somewhere, it's not still, it's not still 2. So that's one open question. And the other is, there are various ways of trying to model sources beyond independence. This is one of them. There are other models. So are there other models, and do they have interesting applications? All right, so with that, I'll stop. Any questions? Yeah.
Applications for state level application for assumptions. Because here from good everything works. Is there a nice roadmap to make it applicable to RL?
Right. Yeah, unfortunately, the answer is yeah, I don't know. Yeah.
Because the complexity of the computer now.
Right, yeah.
No further questions.